everybody. First year recess intern. It's been a wonderful summer. So I'll talk about my research today. Okay. So in 1975, Texas established the Harris-Gaveston Subsidence District. And the goal of this district was to use geodetic techniques to study land subsidence in Houston-Galveston area in Texas. And this photo right here is a picture of Baytown, Texas, that has been completely flooded due to land subsidence, and that in conjunction with sea level rise. So the way can you guys hear me? Well, okay. The way my work this summer fits in with what the Harris-Gaveston Subsidence District is doing is actually using InSAR, or radar remote sensing techniques, to study how land subsidence is affecting Houston-Galveston area, which consists of 13 cities. So land subsidence due to due to groundwater withdrawal. So land subsidence is essentially a gradual sinking of the Earth's surface. So when you have land that's subsiding 6 to 100 millimeters per year, and the sea level is rising 3 to 10 millimeters per year, you're going to be pretty much out of luck because the ocean is going to take over the land and you are in the sea. But this photo right here gives an example of what land subsidence is, the mechanics of it. So you have the expansion of clay and silt sediments in this left side of the image, and that occurs when the water in the water table is at its normal levels. But when you extract groundwater from our aquifers, that land surface sinks due to compaction of sediments. And essentially, when the discharge is greater than recharge, you have sinking land. So sinking land is expedited by natural and human processes, such as salt tectonics, sinkholes, and karst settings. For human activity, we have mining, urbanization, and groundwater pumping, which is what my research focuses on. And it's also expedited by fault motions and isostatic adjustment with ice sheets and sediment loading. So the hazards of the hazard. There are plenty of secondary hazards to land subsidence, such as flooding, coastal erosion, delta habitat loss, and sinkholes. Now this map shows the spatial extent of land subsidence in the United States. And as you can see here in the southeast region of the United States, where there's mostly sedimentary deposits, we have a lot of land subsidence in this area, and also along the Midwest where the Ogallala Aquifer is located. There's a lot of groundwater pumping in that area, in most of these blue areas here that we see consistent patterns of subsidence occurring. So my research focuses on this area right here, the Houston-Galveston region in Texas. So here's a little CIA profile of Houston-Galveston, 13 cities, including Baytown, that first image that you saw, and also Gaveston, Pasadena, Sugar Land, and Houston being the largest city with 2.1 million people. Now the Houston-Galveston area consists of 5.7 million people, and it's a very densely populated area located right along the Gulf of Mexico. And also, did you know that more land is farmed in Texas than any other state, so therefore the demand is exceeding the supply. So this is a cross-section of the Gulf Coast Aquifer system. And these shallow water reservoirs right here, the Chacoy Aquifer and the Evangeline Aquifer, are the main water resources for Houston-Galveston. Now, about 1.3 billion cubic meters of water is pumped from this aquifer system yearly, and therefore, used for agricultural purposes, industrial, domestic use, and things like that. So, but there's still an issue. There's a 5-year gap in data since a study done by Q and others in 2015 of this land subsidence happening in Houston-Galveston. And as you can see in these orange, yellow areas, this is where subsidence is occurring, mostly in the northwest region of this area. So these are basically line-of-sight deformation maps created using the following satellite data from ERS, MVSAT, ALOS from 1995 to 2011. And what Q used was this thing called multitemporal InSAR, I'll explain that later, alongside GPS time series data. So my project basically is a continuation of his study by filling in this 5-year gap of data using updated InSAR data alongside GPS observations. And my approach is to detect, measure, monitor, and mitigate this hazard. And the objective is to update, as I mentioned before, using satellite-based and ground-based observations such as GPS and InSAR. And InSAR, most of you may or may not know, because this is UNAVCO, that InSAR is a remote sensing technique that basically studies how elevation and surface displacement occurs on the Earth's surface at the centimeter to millimeter level scale. But with GPS time series data, it helps validate this, these eyes in the sky, right, our satellite data, through interpolating that data and helping us to characterize this land subsidence even further. The main question of the research is, has subsidence remained stable since 2012? Q's study, as I mentioned before, ended in 2011 with the ALO satellite. So my data is going to continue on from 2012 up until the present day, 2016. Here's a little InSAR 101. So essentially, you have a radar satellite, right? You have a first pass and you have a second pass. So this first pass, think of it like a cell phone, right? It takes a photo of the Earth's surface, a particular point on the Earth's surface, in this case, a volcano. And then on the second pass, it takes a second photo of that same feature on the Earth's surface. When you difference the two images, you create an image that measures the phase difference or the range change. So the range change is essentially the deformation that's represented in the scene. So range change is pretty much, if you have a range increase, therefore you have an increase between the distance of the sensor and the ground surface, and a range decrease is the range increase is an increase in the distance between the sensor and the satellite, and the range decrease is the decrease in the distance between the sensor and the satellite. So therefore, range decrease is uplift, and range increase is subsidence. So phase is defined by basically this surface deformation that we see on the Earth's surface. And this equation was created by Berardino and others in 2002. So phase, you have to take into account the azimuth, which is the satellite direction, and the slant range in pixel coordinates. You also have to take into account the surface displacement in the radar direction, the radar wavelength, and in this case we use Sentinel-1A data, which has a radar wavelength of 5.6 centimeters. A perpendicular baseline, which is the orbital separation between the two passes. The SAR look angle, and the topographic error, which is, it should be pretty low for the Houston-Galveston area because it's mostly a flat surface. Atmospheric phase delay effect. These scenes, even though radar is very good at penetrating all weather, also it's good for using, for analyzing nighttime data, still, atmospheric effects still have an impact on the scene, so that's something we also have to account for. And also phase due to other noise sources. And we use this equation to process scenes, and therefore to get rid of noise and atmospheric corrections and DEM errors, we have to apply the short baseline subset approach, which was also implemented by Berardino in 2002. So this network that you see right here is called the Sboss Network. This is a network of 138 interferograms which basically measure the phase or the change in deformation. We pre-processed 25 Sentinel-1A descending scenes, and as a result, we got this network of 138 subset pairs. We set the critical baseline spatial baseline to 100 meters and the temporal baseline to 100 days. So by setting these baselines to a particular threshold, having this small baseline helps to produce high-quality interferograms that will show the deformation signal without the effect of DEM correction and atmospheric error. But what's happening beyond Houston-Gaveston? So this is hydrologist Michelle Sneed of the USGS, and she was basically showing, the amount of subsidence that has occurred in the San Joaquin Valley in California. And as you can see here, over 48 years, from 1965 to 2013, we have 7.3 feet of subsidence, which is pretty extensive. Now, in this animation, courtesy of NASA, it also shows the power of using geodetic techniques to study land subsidence. So these are the cities surrounding the subsidence area, and blue represents flat land, and as it moves across the color spectrum from pink to yellow, we see land subsidence occurring in this area. And this scene was created, this time series data was created using ALOS Palisar data. And from 2008 to 2011 is not a very long time, but this shows us how much subsidence can occur within a very short period of time. And there are also other places that are dealing with subsidence. My colleague Jose, who was studying the Ganga Brahmaputra in Bangladesh, to also answer your question earlier, yeah, definitely there's a lot of land subsidence happening in that area. Right here we also see in Las Vegas, Nevada, there's subsidence occurring, and also New Orleans, Louisiana. But where are we now? So this is just a reminder of the subsidence that's occurring in this region. But we have preliminary data. So my results to date. So as you can see right here, I mean, it's not a whole lot, but these are 6 images of that 138 stack of interferograms that I produced over the summer. And these are line-of-sight deformation maps showing displacement in millimeters. The blue areas represent subsidence, and the red areas represent uplift. Now, we still have yet to apply the atmospheric and DEM corrections, but we are confident that we know that subsidence is occurring in this area. It's just a matter of determining whether it has remained stable. Are these rates stable? Have they, decreased? Have they increased? We don't know. So the master image, as you can see, all of these images begin with July 18th, 2015. So with InSAR, you have a master image, or the first pass of the satellite, and a reference image, or the second pass. So all of these images, July 30th, August 11th, August 23rd, they're all relative to the master image, July 18th. So this is what we have thus far. There will be more data to come. Stay tuned for the AGU conference in December. But yeah, it looks really promising. It looks very promising to see what's happening in the Houston-Galveston area, which is located right here. And this is only one subswath of the scene. Therefore, our next steps are to apply the Sboss time series processing to the stack of interferograms, applying the atmospheric and DEM corrections, and to reduce that signal-to-noise ratio to produce high-quality interferograms, and to complement that data with GPS, continuous GPS systems. But for the broader impact, we want to create stronger monitoring systems, but more importantly than that, we also want to better manage our water resources, or else we are doomed, to say the least, because it's extremely important, and that's why I feel like my research is, our findings will be a huge contribution to continuing and updating InSAR data for the Houston-Galveston area. And for acknowledgements, it's been a very productive yet challenging summer, as we all interns know. Thanks, Scott. I've bothered you many times when my computer was on fire, and as you can see in the little GIF right there. But I also want to thank you, NAVCO, RESESS, NSF, and all the other people, and UNAVCO staff. Melissa, thank you for the chocolates when it was stressful, for helping me out. And yeah, it's definitely going to be a continuation of my research for grad school. So, questions? Questions, comments?
Oh, okay, great. So when you're applying the atmospheric correction and then the DEM correction, do you think that that's going to augment some of these results, or do you think it's going to minimize the amount of subsidence that you found? Like, do you have any kind of kind of predictions of how those corrections might affect your data?
I don't think it's going to augment my results. I think it's going to enhance the deformation signal that I'm looking for.
Oh, okay.
But we'll just have to see what happens once those corrections are applied to see what's been happening in that area.
Great, thank you.
All right, thanks. I think Andrew has a question.
Hi, thanks for a great presentation. I didn't quite catch the color scale that you're using on the 3-panel image just before you got into the InSAR data. And I think that 3-panel image was showing the summary of subsidence from Q's work. And I wonder if you could explain how your initial processing, how the trends are in the subsidence that you're finding compared to the earlier work.
I got the first part of that question. I didn't get the second part.
So I think Andrew was asking about the comparison between what Q found and the trends that you're starting to see in your results.
Okay. So, well, the results aren't complete yet. This is just our preliminary data that we've processed. So the line of sight deformation maps that you saw more than likely have some type of deformation signal in them, but we can't quite see that right now because of the atmospheric corrections in the DEM error that we have to fix. So we're hoping, not that I'm hoping that Houston-Galveston is going to keep subsiding, but we're hoping that we can see that signal clearer, you know, when we apply those corrections. So right now it's too soon to say.
Okay, another question, Jenny.
Hi, great presentation. I was wondering if there is any physical evidence of subsidence in the Houston-Galveston area. So are there, you know, roads that are offset or houses, or is it more of a, you know, a large scale kind of subsidence where everything is uniformly going down?
Well, not everything is uniformly going down. In that study by Q, it's mostly happening in the northwest region. Houston, the city itself, is actually slightly uplifted compared to those areas. But there is physical evidence of that done by a previous study by Bawden and others in 2012 at the USGS. And they have water level data checking the Chacoy and Evangeline aquifers to see what's been happening there. And also GPS data has been done by the Harris-Gaveston Subsidence District, seeing what's been happening in those regions too. So yeah, there's evidence available for that. But it's not uniformly sinking.
Okay, this is a very popular topic. I think we have time for one more comment.
I can just add anecdotal. So I have relatives that live in Houston, and during the Texas drought a couple of years ago, a lot of the homes actually had differential sinking underneath, and so there's a lot of cracking of foundations and a lot of actual structural damage. So I think on the micro scale, there's evidence that's probably collaborated with the insurance companies.
Yeah, Baytown is a perfect example of that. I mean, in the image that I showed you, a lot of areas are going through that. And even in other places around the world, it's very obvious. I mean, even in my hometown, where I grew up in the Bronx, New York, there's a city called Co-op City, and it's located on top of this marshland. And they've been doing some pumping in that area, and it's obvious to see all of the cracks in the ground and how it's been subsiding over the years, but no one's studying the area. So that's why it's important for us to find these locations where there are densely populated areas and take advantage of these techniques to see what's happening and maybe implement some change.
Awesome. Thank you, Ayanna.